So we've talked about shape of graphs and we've talked about the center of graphs. We need to talk about how we can quantify with numbers how spread out a graph is. And that's going to be either standard deviation or IQR. For symmetric distributions, the mean will be useful. So we'll talk about a number that shows us the average distance from the mean. That's exactly what standard deviation is. If you remember nothing else from this whole video, remember this. Standard deviation is the average distance from the mean. However many stars you need to write on your notes, draw them. Okay, that's really important. Because in math, we talk about standard deviation. We throw it around all the time, but it's not super obvious what it represents. If we unpack those two words together, standard deviation, a deviation is just the difference between one value in a data set and the mean. Okay, so standard deviation is the standardization of that, the averagization of that. That's not a word. Averaging all of those deviations, basically. Okay, how far is each thing from the mean? And it's more useful for symmetric distributions. So let's kind of go through this. This is a tall order. There's a lot of math in finding the average distance from the mean. We're going to have to find all the different distances from the mean and then average them. And there's kind of a weird middle step as well that we'll get into. So let's say that there are 4 students sitting at a table with the following ages: 22, 2 19-year-olds, and 36. First off, this is not symmetric data, so standard deviation is not super meaningful here, but it's good for some practice. Okay. Also, if you're curious, if you look at students' age in general, that is going to be skewed to the right. The big concentration is going to be on the younger side. Then there's going to be a smaller number of older people as well. Okay, so calculate the mean age of the students. If we want to find the standard deviation, we need the mean. Why? Because the standard deviation is the average distance from the mean. All those stars. Sorry, that was a little too excited for me. We should keep math videos nice and boring. So how do we find the average distance from the mean? We need the mean. So let's get some practice. Sum all of the x's and then divide by how many there are. So the x's, the data values are 22, 19, 19, and 36. Remember that I said if you ever want to find the median, the data needs to be ordered. The mean, it doesn't really matter, but it might just be a good habit to be in anyway, to order the data, just to be safe. And now we could easily see that the median is going to be the middle of these two numbers, 20.5. We don't need the median here. So add them all up and divide by how many there are. Use our handy dandy calculator. Find that out. Use parentheses, 19 plus 19 plus 22 plus 36. All divided by 4. The average age is 24. Okay. X bar is 24. We need to find the standard deviation, which is the average distance from the mean. I'm going to say that a million times. So we needed the mean. Now we're going to find all the deviations. How far is each data value? Again, anytime you see X, think data value. We need to find out, okay, how far is each data value from that mean? So let's find them all out. There's going to be a bunch of X's, right? We have 19 minus the average. We have another 19 minus the average. We have a 22 minus the average. We have 36 minus the average. These are our 4 deviations. Simplify, -5, -5, -2, and 12. This says that there are 2 people that are 5 years younger than the average, 1 person who's 2 years younger than the average, and 1 person who's 12 years over the average. Okay, so these are our deviations. Now, I said you can think of standard deviation as the average distance from the mean, but distance is a positive thing. Okay, so we need to make these positives. And there's two really common ways of making things positive in math: absolute value, which literally just gets rid of the negative, and squaring. The problem is once you get into more like theoretical math with like analytical components, absolute value is a really kind of ugly function. It does not behave nicely, whereas squaring does. So to turn these positive, we're actually going to square them. Okay? Because absolute values make math awful, basically. Even though absolute values are really easy to do like by hand, mathematically, when you get into like calculus and further beyond, absolute values cause a lot of problems. Okay, so let's find the squares of the distances. That's what we need to do next. Well, the distances, we knew those. Now we just need to find the square of the distances. The distances, the deviations were -5, -5, -2, and 12. We just need to square each of those. That's what we're going to do next. There's a lot of steps here, okay? So when we square each of these, -5 times -5 is positive 25. A negative times a negative is a positive. That's why we're squaring it, because regardless, we'll have just a bunch of positive numbers. So now these are the squared deviations. Okay, are we almost done? What's step D? Okay, great. We can finally average these squared deviations. That's great. So we need to find the average of all of these guys. But there's a wrench in the plan, because there's a complicated thing in statistics called degrees of freedom. We're not going to go into that. That's way outside the scope of this class. But to find the average of these deviations, we actually are going to divide by n-1. We're not going to divide by 4. We're going to divide by 3. We're going to divide by 1 less the sample size. Okay? So we're going to add them up and divide by 3 here, not 4. I'm willing to talk with anyone who's really curious about this, but it really goes down into a big rabbit hole. And it is definitely outside the scope of this class. So let's add them all up and divide by n-1. We need to add these up. 25, 25, 4. And 144. And divide them by n-1, which is just 3. So what happens when you do that? Let's use our calculator again. We're going to say 25 plus 25 plus 4 plus 144. Divide that by 3. And we get 66. Again, it's really good practice to be, like, you can use your phone as a calculator, but it's really good practice to use GeoGebra's calculator as well. So it could be a great opportunity to pause the video and actually do these calculations along with me. See if you're getting the same thing. See if you can get it to look the same way that mine's looking, and try to figure out or ask questions if you do run into any issues about that. I would highly recommend doing that. Okay. So the average of the squared deviations is 66. Are we done? Well, we're told that the average of squared deviations is called the variance. That's not what we wanted. We wanted the standard deviation. We wanted the average distance from the mean, but we have the average squared distance. Well, how do you undo squaring? We're almost done, because we just need to take the square root now. We have everything squared, and we need to undo that with square roots. So we're going to do that, and that'll give us our standard deviation, our average distance from the mean. So what's the square root of 66? I don't know. Some number a little bit more than 8. On GeoGebra, you can write SQRT and then a parenthesis sign. Press enter. 8.12 about. And again, if we look at this, What were the distances? What were the deviations? The distances were like 5, 5, 2, and 12. The average distance being 8, a little bit bigger than we might expect. That's because we're squaring and unsquaring, basically. We can think about 8 as the average distance from the mean. Okay. Remember, average is affected by outliers. So this 12 is really making this average distance, the standard deviation, a lot bigger than we think it should be. Which is why we mostly use standard deviation for symmetric data. But anyway, we can kind of summarize this. We can kind of summarize it and say, the average age of these students is, we said 24 years old. And it will differ by about 8 years on average. So that's how you can kind of interpret standard deviation with kind of this sentence right here. We expect 24 years on average, and make sure to include the units. The units here are years. Okay, and that's what we've got here. And that's kind of what we got going on for standard deviation. We'll do some more with it. We'll get some practice. We'll show you how to use a computer to help. Again, this whole unit is introducing concepts and then using technology to help us with them. But you can see where these are coming from. Standard deviation is the average distance from the mean. So we had to do those step by steps. Find the deviations from the mean. We had to make them positive. We had to take the average. Then we had to unsquare them. We'll formalize this in the next video. Okay. I want to end with a small summary. Remember that symmetric data, we want mean and standard deviation to decide center and spread. That table that we got back here. And then skewed will be median and IQR. We haven't talked about IQR yet. So remember that. And skewed data kind of messes up the mean and messes up the standard deviation. So as a kind of summary of what we did, we found the deviations. Those were the data values. Remember, X is data value. The data values minus the mean. We found those squared deviations. We took the average by adding them all up and dividing by our degrees of freedom, which was the sample size minus 1. And then we undid all of that squaring by taking the square root of our answer. When we found this average, that's known as the variance. That's called S squared for sample variance. And sample standard deviation is called S. Quick note, there are some very similar formulas for population variance and population standard deviation. Again, this is a lowercase sigma. I said that this sum sign is also a sigma. It's a Greek letter. It has lowercase and uppercase, just like our letters. So this is what we do if we want population variance. So what's the difference between sample variance and population variance? When do we use which formula? Well, most of the time we'll use sample variance. Okay, that's why the population is in parentheses. But you'll use this when data is the whole population. You'll use it when the data is the population. You use this when the data is the sample. Okay, so sample standard deviation comes into place when your data is a sample. Population standard deviation comes into place when your data is the population. Okay, and the only difference between these two formulas is what your degrees of freedom are, that denominator, which again, don't worry too much about that. Usually we'll deal with this, but sometimes we'll have to use that. Let me know if you have any questions. This is a little bit more math intensive, but don't worry, technology is coming. You're just seeing the behind the scenes. You're seeing the behind the scenes before you see the movie, which is a little weird. But when you see the movie, It's going to be real impressive now. Bye-bye.